Swayam Prabha. Digital India. Educated India.
Okay, so very good morning to everyone, and thank you for registering for this course, which is on characterization of heterogeneous catalysis, bulk, surface, in situ, and operando methods. So I'm very excited that we have more than 45 participants, roughly 50% here present in person at IIT Madras, and about another 20-25 joining us from the Zoom meeting link. Okay. So this is the very first course. So we will go over only a brief history of catalysis and what is the role of catalysis that is going to be in 21st century, and then just get into touch of some of the very basic concepts like the nature of the active sites and the active site dynamics and all these things. So I am Dr. Sagar Saurabh. I am an assistant professor at the Department of Chemical Engineering here at IIT Madras. So for today, this is going to be our lecture outline. So we will start with a little bit on the history of catalysis. Then we will look how catalysis changes our lifestyle and the modern age human society in 20th century, and what is the role of catalysis that is going to be in the 21st century. Then we will go over a little bit as on the classification of catalysts, and we will talk about the length scales of the reactor, the catalyst particles, as well as the active sites. And finally, we will go over a brief idea about the dynamics of the active site, which is going to be the major part of this full course, and then talk about the tuning of the active sites, how we can tune the active site to improve the catalytic activity as well as the selectivity towards the desired product formation. So before I start, I just want to pose a very general questions to all the participants online and offline, is that what do you think, like when was the first instance of the catalysis that has been known to the humankind? You want to take any guess? 50 years, 100 years, 200 years? Any guess? No? Just give it a guess. Okay, so I'll give you the answer. So it was almost 10,000 years. Now, if we go back to the age when we are preparing beers or wine, like brewing, so what we are doing is that there were some yeast which are enzymes, and they have been added to the fruit juice or some other materials, and over the time they age, and because of the fermentation processes we were getting the wine and the breweries. And similarly, there are other examples at that time which was on the baking. So on the baking part, everyone is familiar with dough or the sourdough, and at that time what was happening is that if you take a small amount of the old dough which has created some yeast inside it, and we mix it to the fresh dough, what was happening is that because of the fermentation, the bread was rising and all. Similarly, there were a few other examples like leather tanning. So the leathers were coming from the animal skins, and if we can add a substance from a plant, that can actually increase the lifetime of that leather and suppress the degradation of the leather to a large extent. And similarly, the cheese making. So these are some of the first instances where the catalysis was known to the mankind, but the mankind was never aware that these are actually some scientific processes through which we can do the transformations. And these comes under the category of biocatalysis, where some microenzymes and yeast type of material we are doing some chemical transformation. So in the modern days, coming back to some 200 years back in 1798, that was the first instance when we looked at the homogeneous catalysis, where we were doing some acid hydrolysis of starch. So some dilute sulfuric acid, when it is reacted with the starch, we were getting sugar type of molecules. So that was the first instance for the homogeneous catalyst, and then the first instance for the heterogeneous catalyst or the solid acid catalyst was on the dehydration of ethanol. So if you pass some ethanol vapor on a hot aluminum substance, then it will just convert to ethylene. And moving forward, the very first practical use of the heterogeneous catalysis came in 1825, where the very famous Doberneer lamp was popular in Europe. It was so popular that within 5 to 6 years, over 1 million of such lamps were sold throughout the Europe. So I will just explain this thing a little bit. So before the Doberneer lamp, producing or generating fire was a task for humankind. I mean, they were going through the friction and all to generate some fire, and then letting that fire off was sort of a crime. So what Doberneer did is that he made this kind of the lamp, which was very handy, and then people can take it with them. So they have a small chamber where sulfuric acid was put, and then there was this zinc ribbon, and if with this lever you can actually submerge this zinc ribbon or dip this zinc ribbon inside the sulfuric acid solution. So what will happen is that the zinc will react with the sulfuric acid, and what product we are expecting here? When zinc reacts with sulfuric acid? Zinc sulfate and hydrogen, correct? And that hydrogen goes through the platinum ribbon that is connected at the top of this lamp, and we have oxygen in the air, we have hydrogen, and both can react on the platinum foil or the platinum ribbon to produce some fire because of the oxidation reaction. So now, before this Doberneer lamp, we are actually having trouble in creating fire, but after this, now we can actually make fire at our wish. So that was the very first application of heterogeneous catalysis. And then moving forward, we have Berzelius, who is typically known as the father of the catalysis, who formally told what catalysis is. And according to his definition, so they said there is a class of reaction that takes place only in the presence of a substance which remains unaffected during this transformation. Okay. From that, let's just go what we saw in the 20th century. So in the 20th century, there was real trouble in getting nitrates which was produced from the nitric acid, and these nitrates are used during the formation of explosives for the wars and everything. So what Fitzherbert did is he did the ammonia synthesis on a magnetite, on a magnetite type of catalyst, where at high pressure and high temperature you react hydrogen and nitrogen to get ammonia. Now once you have the ammonia, much before the Haber-Bosch process, the Oswald in 1903, he showed that how ammonia can be oxidized on platinum to form nitric acid, and then formation of the nitrates, and those nitrates can be used for the war. So because of this ammonia synthesis process, the World War I lasted for more than 4 to 5 years. Without that, it could not have lasted for more than a year. But now that is not the exact application of the ammonia what we are seeing in the modern day. From the ammonia, we are actually producing the fertilizers, and with the rising population of the world, this fertilizer is actually helping us to generate enough amount of food to feed the population across the world. And here is just one example where we are looking at the energy required for the production of ammonia and how it evolved over the years. So for electric arc processes and cyanamide processes, the energy requirement per ton of the ammonia production was pretty huge. But then during the 1920s, 30s and 40s, which was the early stage of the ammonia synthesis, the energy requirement came down a lot, and with evolving catalyst over the past 100 years, now we have much less energy requirement because of the high efficiency of the catalyst. But still, ammonia production is one of the most energy intensive process in the catalysis community at present. Okay, and here I have highlighted few of the other major milestones that were achieved by catalysis and the catalyst science in the 20th century. Some of those are like in 1923, there was like methanol synthesis, which was the very first attempt for the C1 chemistry that we are seeing today. And then zinc and chromium oxide based catalysts were used for production of the methanol, and similarly for Fischer-Tropsch processes were appearing at that point, where either cobalt or iron oxide catalysts are shown to be capable of converting syngas to the hydrocarbons and alcohol, such that we have the commodity chemicals as well as the energy requirement for the modern society. And in 1930s, we were able to do the catalytic cracking such that the heavy naphtha can be cracked into the lighter hydrocarbon on an aluminum chloride type of catalyst. And then alkane oligomerization happened, which was a silicophosphate type of material where phosphorus pentoxide was about 60% and silica was about 40%. And this oligomerization was converting low alkanes to longer chain alkanes to increase the octane number of your gasoline or the petrol, such that your fuel efficiency and the fuel quality is increased, and that contributed to the modern day transportation fuels and everything. Another major milestone was ethylene oxidation to form ethylene oxide, which was the precursor for formation of ethylene glycol. Now, this ethylene glycol is a very famous antifreezing agent and it has many other applications as well. One more notable thing is the polymerization, where the plastics for daily use as well as for the material synthesis and engineering applications were able to be built. And two scientists, Carl Ziegler and Giulio Natta, both were awarded Nobel Prize for that, for the preparation of this Ziegler-Natta catalyst, where ethylene and propylene were converted to polyethylene and polypropylene over a titanium chloride type of catalyst. And currently this Ziegler-Natta catalyst has some added component to it in the form of the magnesium chloride. Another breakthrough came in as the zeolite type of material. So these are some of those synthetic materials which were first found during 1950s and 60s, and aluminosilicate compounds, and they are well known for their acidic behavior as well as very precise size and porosity nature, such that the reactivity and the product selectivity can be tuned according to the nature of the reaction or the type of the products that we want to see. And one major breakthrough on the zeolite catalyst was the formation or the synthesis of the GSM-5 that was about 1974. And in modern day, any petrochemical or refinery industries, especially the refinery industries, these GSM-5 based catalysts are very popular. So there is a comprehensive list for what are the different milestones over the 20th century. So I have made some course materials, and when we are going to share the slides with all the participants towards the end of the lecture, I will just share that comprehensive list in 1910s, 20s, 30s and so on over the whole 20th century. What are the major achievements by the catalysis science and the typical reactions and the type of the catalyst that was used for that particular reaction. So now moving to the current stage, now the application of the catalysts are vast. So here I have divided it into 4 different parts. One is for the petroleum and energy sector, where we have the transportation sectors because of the cracking of the naphtha and the crude oil to get gasoline and diesel kind of fuel, and as well as aviation fuels. And we have commodity chemicals, which are the different types of polymers, additives, cosmetics, as well as coating materials and all. And this happened because of the polymerization processes and all. One other category comes because of the pollution control. So we have automotive vehicles, and SOx, NOx and hydrocarbon release from the exhaust of the automatic vehicle is very common. So if we have a 3-way catalyst, we can actually convert that to a less harmful chemical or the compound which can be released to the atmosphere. And of course, there is a big contribution in the drugs or the pharmaceuticals and the food sector. So dairy, medicines preparations, as well as some beverages and all, and catalysis has application in those areas as well. So typically, whatever the manufactured products these days that we are seeing or using in our daily life, more than 85% of those processes are coming from the catalytic side. So a catalyst is involved in synthesis of those processes, and only about 15% are coming from non-catalytic processes. So it is obvious that the market of the catalyst is huge. So the direct catalyst market in the whole world is over 20 billion US dollar, with a cumulative annual growth rate of about 4%, whereas the associated market, like the different products or the steps where we are going through the catalysis processes, it can be easily 20 to 25 trillion dollar. And this is just a question, like any guess, what is the economy of the world at present in trillion US dollar? Roughly? Around 100. So about a quarter of that economy is coming from the catalyst and catalysis science. So that only says that how important is the catalyst and catalytic processes in our modern day society, and that is not going to change in the 21st century as well. It's still going to play that huge role in this century and for the coming centuries as well. So okay, so this is one sentence that I took from Adam's Topics and Catalysis paper. So I'll just go through it and give you a minute type of thing just to process it in your mind, and then we can discuss it in the further slides. So it says, if the society does not properly understand the complex relationship between the technology and society, and if that understanding is not applied through the process of creating new technologies, then we will end up creating less than optimal technologies for supplying energy and materials. Okay. Again, I apologize for this brief interruption. I hope everyone can see my screen again. Okay. So, here I have highlighted, I mean, among many modern day problems where catalysis can be used to solve some of these problems. This is, I have just highlighted and segregated into 4 different parts. The first part is that with increasing human populations, our dependency on the fossil fuel is increasing day by day, and what is that bringing to us is that the natural sources are depleting, as well as because of heavy reliance on these natural sources, we are generating a lot of carbon dioxide and contributing towards the global warming and some of those other issues. So one area where catalysis can definitely contribute, and we all are working in that direction, is that transition from the fossil fuel to the renewable as well as to the circular economy, and some of these involve like recycling of biomass issues, and from waste and carbon dioxide recycling to form some fuels and chemicals. The other one is that for all the processes that we developed in the 20th century, so that time we had a need, and based on that we developed some catalytic processes, but some of these processes are not hazard free. I mean, they have some carcinogenic material. For example, high temperature water gas shift reactions, you have chromium present as one of the ingredient, and this chromium is carcinogenic and it endanger the human life and the society. So one other direction could be transitioning to hazard free, waste free and energy efficient manufacture of the materials and chemicals. The third one could be a tool for interconversion of energy vectors. So we have renewable energy at our disposal at present, but can we convert that renewable energy into a form where we can store energy and then use at our wish? One biggest example in that area is the hydrogen economy, where the renewable energy can be used for water splitting and production of the hydrogen, and then after the production we need to store and transport those hydrogen to be used as our energy requirement is rising. And then of course there are new catalytic technologies which are evolving day by day, and we need to combine science with engineering. With this interdisciplinary approach, we will be able to solve majority of the problem. And again, I have prepared a very comprehensive list of what are some of the areas where the catalysis can help in the 21st century in solving many of these issues, and I will be sharing those things with all the participants at the end of the course along with the lecture notes and all. Now that we know about the future of the catalyst and all, now let's just go back to the basics a little bit, because we have participants from all different backgrounds. So just to bring all of them on the same page, so if I ask what is catalysis, the first definition was given by Berzelius, and it's a Greek word. Kata means wholly and linen means loses. So it breaks something or loses something, and from there the word catalysis came to the process. And then what he proposed is that the catalyst possesses a special power that can influence the affinity of chemical substance, or in other words, it can help in converting one substance to the other without undergoing change. And some of those things were modified, and before Berzelius, Oswald in 1895, he suggested that a catalyst is something that accelerates the chemical reaction but without affecting the equilibrium. So catalyst cannot change the equilibrium, but it can actually help the rate at which you can go towards the equilibrium. In the modern day, it says that it increases the rate of attainment of equilibrium, which I just said, without itself undergoing a change. But now in the modern day, with a different kind of characterization technique at our disposal, this is a question like, does catalyst really not change during the process? And that is exactly where we are going to focus throughout this GAN course with in situ operando bulk and surface characterization techniques, to look at what are the transformations or the modifications that is happening to the catalyst because of the reaction environment and because of the temperature, and what dynamic sites are forming during the process. So moving forward, so the catalysts can be classified into 4 different parts. These are the major sections. One is a homogeneous catalyst, which was in the 19th and the 20th century are famous. So these some of those acid-base catalysts and the transition metal complexes come under these class of catalysts. Then there are biocatalysts, where enzymes, yeasts, and other microorganisms cause some chemical transformation to happen. And then there is heterogeneous catalyst, which is the state where the catalyst and the reactant are in different phases or different medium, and some of the examples are either bulk oxides, bulk metals, supported oxides, supported metals, and we will see some of those examples. And then in modern day, there is something called heterogenized homogeneous catalyst, where we take a homogeneous catalyst, and these are typically these transition metal complexes, and we stick them on a high surface area support such that they behave as heterogeneous catalyst. And among all these different types of catalysts, currently in industrial processes, more than 80% of the catalyst that is in use are coming from the heterogeneous category. About 17% come under the homogeneous category, and about 3% comes under the biocatalyst category. And then the homogeneous catalyst category is continuously being replenished or replaced by the heterogeneous catalysis. So the contribution from the heterogeneous catalysis is increasing day by day. Maybe someone has your microphone on. So these are some of the example of those enzymes and cells which comes under the biocatalysis. We have the substrates and we have the enzymes which are connected to them. We have the enzymes which are present in the covalently cross-linked form. We have enzymes which are not chemically bonded but physisorbed on a certain substrate. And then of course we can have enzymes which are trapped inside polymer matrix, and as well as encapsulated in microbial form. So these are different kinds of enzymes and cells in different forms that are used in catalysis these days. And similarly, some of the heterogenized homogeneous catalysis where we have the atomically flat surface, which is typically a high surface oxide support type of thing, and we have the ether and the ligand and the metal at the top of that, and some of these dot butoxide of moly, tungsten, and rhenia as an example are shown here. So among the heterogeneous catalyst, we have different classes. So broadly, it can be either a bulk catalyst or it can be a supported catalyst. So the difference is that the catalytic reaction happens on the surface of the substrate, and the bulk has very minimal role to play in this thing, and even if it plays something, then it is an indirect way. And then the supported, what we want is that we want to disperse the active material on a very high surface area support, which are typically either oxide supports or carbon supports, such that we can increase the surface area to the volume ratio type of thing, because as we are going or decreasing the particle size, the surface area to volume ratio is increasing, and more amount of the active material is now available for the reaction. So here I am showing just some of the TEM or SEM images of bulk metal catalyst. So this is a silver catalyst, which is pretty famous for your ethylene to ethylene oxide formation. And in the supported metal category, we have platinum SiO2. This is an example, and some of these supported platinum catalyst or say platinum T non-alumina catalysts are industrial catalyst for dehydrogenation of propane to propylene. And we have bulk metal oxide catalyst, and this is one example that is initially used for the ammonia synthesis process, the magnetite nanopowders. And of course, we have the supported metal oxide catalyst as well, and this is an example of tungsten oxide on high surface area zirconia. And we can see there are isolated species present, which are like one single atom of tungsten center, and there are like bigger clusters are present, which can be in either two-dimensional form like a sheet of tungsten oxide on a high surface area support, or it can be in three-dimensional form like WO3 nanoparticles, for example. So all different sizes and shapes and the facets that is exposed to the surface for to cause the catalytic reactions to happen. So apart from the metal and metal oxides, we have also some examples from metal sulfides and nitrides as well. And one very popular example is moly sulfide, which is either in a bulk form or sometimes this moly sulfide deposited on this high surface area alumina here. And as you can see, some of these fringe patterns or the layer by layer structure of the moly oxides, which are captured in this image at different locations on the surface of L02O3 alumina. Okay. And now that we know the catalyst and all, now let's just look from the perspective, what is the typical size of the catalyst that we are talking about. So if we see the reactor which are operated industrially, they can be several meters to up to 100 meters in their dimension. However, the catalyst pellet inside those reactors, those are of the order of few millimeters, whereas the catalyst nanoparticles are of the order of microns, and the active site on those particles are even smaller. So those are of the order of nanometer or even smaller, close to an angstrom if those are isolated sites or single atom supported things. Now the question is, if something is that small, how can we even think of identifying them, and on top of that understand how they are functioning during a reaction. So this is exactly what we are going to do throughout the course with different characterization methods, both physical characterization as well as chemical probing techniques, to identify these active sites, look at their dynamics, and understand their functioning towards the chemical reaction. And on top of that, here I am showing an example of supported metal oxide catalysts, and this is not any model catalyst. So more than 50% industrial catalysts come under the metal oxide category. And as you can see, these catalysts have many different types of sites. So it can have redox sites, it can have different types of acid sites like either a bronze acid site or a Lewis acid site, or it can have vacancy sites as well as some of the defect sites. And all these sites, they may or may not take part in the reaction, and they may or may not contribute towards the desired product. So if one site is favorable for conversion of your chemical to the selective product. The other site that is present on the same catalyst at the same point may be responsible for the formation of the side product or the undesired product. And in some cases, it may happen that we have two different types of sites. Those are playing a like synergistic role in taking part at different step of a big complex reaction. So unless we identify these sites properly through different characterization methods, we won't be able to understand how these sites are working and contributing towards the reaction, and we won't be able to understand the molecular level structure function relationship, which is, by the way, utmost importance for designing a better catalyst. Because catalyst design comes from the fact that we understand how a catalyst works. And this is something that we are going to cover throughout this course through different characterization techniques, which are by far very, very powerful in looking at the catalyst structure and the dynamics in reaction environment. And on top of that, these are some bulk and supported metal catalysts, for example, and although we think the surface to be smooth, in reality they are not. So there can be a terrace site, which are like the planar surfaces, and on that terrace site also the energy diagram is not a continuous function. So it's continuously changing as we are hopping from one side to the other sides, and there are a bunch of different hop sites. So for example, on the right sides we have a diatomic molecule which is adsorbed on the surface non-dissociatively, and there are multiple locations at which it can adsorb. For example, it can be on top of one atom, it can be in between two atoms like in a bridged form, or it can be dissociated and attached to two neighboring atoms like in a bidentate form type of thing. And on top of that, there can be a defect site which is a hole on the terrace. There can be step sites which are, by the way, energetically sometimes favorable for the catalytic reactions because of their energetics, and we can have king sites which are sort of the corner sites, and on the terrace instead of a hole we can have an extra atom which are typically called add atom, or we can also have add islands and all these things. And these are some of the defects that we see in a real catalyst, and they play a crucial role in the catalytic processes. So some of these things that we are going to see will come under this category, identifying all different types of defects as well as the regular sites and all. And then we have something called the active site dynamics during the reaction. So this is just a glimpse how the site can change when it is exposed to the reaction condition. So at the center, what I am showing schematically is a fresh catalyst, which is a supported catalyst. You have a large surface area support, and you have the active metals or metal oxide deposited on that surface. Now this restructuring can happen, which is shown here, where the metal or metal oxide particles in isolated or in cluster forms and three-dimensional nanoparticle form that is present on the support, they can transfer to different structure, which is different than the one that was present on the original catalyst. We can have leaching, that is because of the harsh reaction environment, some of these active materials are flying off the support surface, and that can cause some catalyst deactivation. We can have sintering, that means some of these smaller size particles are coming together to make a bigger particle. And we can have a support transformation or the support hydrolysis or collapse, where because of the reaction environment, the support structure is either changing or collapsing in terms of the surface area and all, which is detrimentally affecting the catalytic processes. On top of that, because of the reaction conditions, there can be different types of catalyst deactivation. One example is carbon deposition. So if you are forming some carbon, they can actually coat over the active materials that is present on the catalyst, and then that can hamper your catalytic activity over time. And of course, we can have some gases which have a much higher affinity to stick to these surface active materials, and because of that, the actual reactant which need access to this active reactant are not able to access the active site for the chemical transformation. So this is an example of poisoning. So here I am showing just one example for a sintering process. This is an environmental TEM image for a catalyst that is nickel deposited on magnesium aluminate, and we are seeing the sintering of nickel particles. So as a function of time, and the condition is high temperature, that is 750 degrees Celsius, and we have both water and hydrogen present. So at time 0, we can see the darker atoms, which are darker points here, which are the nickel particles. They are spread over the surface of this magnesium aluminate, and over time, after 10 minutes, we can see some of these nickel particles now have grown to a bigger size, and the smaller ones have disappeared from the surface. And given more time under the reaction conditions, now those small particles are almost vanishing. So this is an example how through characterization under reaction conditions we can see, or close to a reaction condition, we can see the transformation of the catalyst surface and understand how the catalyst deactivation is happening. So coming back to that length scale problem, I'll start from here again. I hope this is better. So we have different types of active site dynamics or the catalyst dynamics, and in the according to the length scale as well as the duration which it may take or typically takes during a catalysis processes. So some of these things like sintering as one example we saw in the previous slide. So there are other things like the active site dynamics that happens really quick and at a very small case, and the segregation that also happens at the active site, so at a small scale, but it takes a longer time. So the duration is of the order of few hours. Similarly, the sintering of the particles, it's slightly bigger because it happens at the catalyst nanoparticle level, but it also takes a longer time. And some of the transport regimes within the sites, these are of the order of microseconds, where of the order of hours we have the transport inside the reactor, the limitations and all. So apart from the active site dynamics, we also have the tuning of the active site. So just because the reaction environment, that is the temperature and the gas environment, can cause the active site to transfer to a different type than well compared to the fresh one, can we actually do some of these things in a controllable way such that we can synthesize a better catalyst which was not there at the synthesis point. So some of these are like we have control over the size of the particle. We can create small size supported metal catalyst, and then we can tune the particle size and see what is the typical effect of particle size on the catalytic reactions. We can add a secondary element like a metal alloy type of thing, and we can see how that is affecting the catalytic reactions. On the other side, we can change the support material, because these metal particles or the metal oxides, they are going to interact with the support in a much different way, and changing the surface area, the compositions or the morphology of the support can actually do a lot change in the catalytic reactions. Similarly, we can do a bunch of different type of treatments. We can do a thermal treatment, we can reduce the catalyst, we can oxidize the catalyst, or we can go over a cycle of reduction and oxidation such that we can reach a step where the final catalyst or the structure of the catalyst is more active and selective towards the desired reaction as compared to the fresh catalyst. We can have overlayer deposition, or we can have adsorbate mediated interaction of the oxides with the metal particles. So for the last one, we will just see one example. So here is a catalyst that is copper zinc oxide deposited on alumina. Now this is an industrial catalyst and used for many different types of reactions. So for low temperature water gas shift reaction, for methanol synthesis, as well as methanol steam reforming. So here in this example, what we are seeing is that how we can tune the catalyst either by reduction or by some different mechanism where we are treating the catalyst in a very specific environment, and we can cause some change to the catalyst structure and see what is the final effect of it on the catalytic reactions. So we took this copper zinc oxide alumina catalyst which is shown here, and then it was treated or say reduced in hydrogen environment for 60 minutes. And what we observed is that even after reduction in hydrogen environment for 60 minutes, we can see the copper nanoparticles and the zinc oxide particles are separated from each other, and they are coexisting on the surface of the alumina. But now, if we do a different type of treatment where we reduced it in hydrogen environment for 50 minutes, then we treat it in a methanol plus water plus hydrogen environment for the rest 10 minutes. And under such conditions, what we see is that from the TEM images here, you can see some of the zinc oxide, they are actually migrating to the top of the copper nanoparticles, creating some metal-metal oxide interfaces. Okay, and what is the effect of this migration? As you can see on the time on stream data, first of all, the catalyst activation under the reaction condition is taking the similar amount of time, but over a long period of operation, which is shown here over 40 hours, the catalyst which was treated in hydrogen for 50 minutes and the mixture of methanol, water and hydrogen for another 10 minutes shows a very suppressed deactivation over 40 hours. Only 10% of the initial activity was lost over 40 hours as compared to the one which was only treated in hydrogen for 60 minutes. The deactivation happened say at least 35% as compared to the fresh catalysts. Okay, so this gives us an example how by different characterization we can actually tune the surface of the catalyst and make them more active and as well as stable over a long period of operation. Okay, so that brings me to the end of the first lectures, which was on the overview of the catalysts and all. So just to put few bullet points, what we understood from this lecture is that catalysts and catalysis are still going to play an important role in the 21st century as it played in the 20th century. And then the structure of the catalyst are complex and they are not rigid as was perceived several decades back, but they are dynamic in nature. And today, with the help of modern techniques, different characterization techniques, and the power of these techniques, we can actually trace the dynamic nature of the catalyst and use that knowledge to design a better catalyst.